Okay, so in this lecture, as you can see, there were lots of topics, but some of them I'll try to finish it like today up until here, but we may look at some of them here, and on Monday we will look at this one. Yeah. Okay, so what is support vector machine, or SVM? Actually, SVM is a classifier, a discriminative model. Okay, just like others, that was KNN, LDA, QDA. SVM are another tool to do the classification. But what is special about SVM is that it actually has a lot of features. I mean, it has a lot of functions together to be used in performing classification. For example, if you remember when we look at the K nearest neighbor, or KNN, KNN used the number of neighbors to do the classification. So if most of its neighbors belong to a certain class, it will classify that testing sample to be a member in that class. Meanwhile, for LDA and QDA, we have to come up with a boundary function. It could be a linear boundary or a quadratic boundary, depending on what assumption that you made. So if you remember, naive Bayes, LDA, QDA are actually the same types of algorithm, where you start up with having like the posterior distribution, and then you start to assume that distribution it could be Gaussian, Bernoulli, multimodal, whatever. And if you remember, LDA and QDA assume Gaussian distribution. And then after that, LDA further assumed that the variance of x given y in each class are the same. Therefore, it can reduce the equation into a linear function. But because of that, when LDA make the decision for classification, it's turned out that the decision boundary will also look like a linear line, like just the line like that. Meanwhile, QDA, because it does not make any assumption further, it just used the Gaussian in the naive Bayes algorithm, it's turned out that when you draw the boundary decision line, it will give you like a quadratic boundary. And when it has the quadratic boundary, actually the quadratic boundary was showing to be quite flexible with your data distribution. For example, if your data distribution for two classes are having different variance, QDA will be able to handle that. Meanwhile, LDA will struggle with if your data distribution has different variance because it doesn't fit its assumption. Okay, that was LDA and QDA. But today what we will learn is what is called the support vector machine. Actually, as you can see here, there are linear version and the RBF version. So this probably hints to you that, well, yes, when we talk about support vector machine, there are actually multiple options for a support vector machine. It could be a linear support vector machine. RBF is actually came from the radial basis function. And what are they, right? Okay, before first, I would like to give you a bit of heads up that actually SVM consists of two mechanisms. You can find this in the slide that I just updated recently. I actually provide some handnotes. Okay. Actually, SVM consists of two mechanisms. The first one is a mapping function. The second one is the cutting, or sometimes we call it hyperplane. When we say it's a cutting, that means we are making decision whether or not it belongs to class A or class B, something like that. And that also linked to another parameters in this, that was the thresholding value. Okay, but anyway, let us look at the example of the data distribution. Okay, for example, if we have data distribution that was look like this, right? For k nearest neighbor, actually k nearest neighbor show to be quite flexible. Like even data distribution that you have initially, like it's like this, like the red points is surrounding and the blue point is at the middle. K nearest neighbor can still make that decision by using the training data sample, and then it can classify a testing point that is thrown in maybe into its algorithm by finding the nearest neighbor to that data sample. And it's turned out that its boundary decision is going to be curvy as the way that the data sample structure. QDA is the same. QDA can form the oval boundary because it used like a quadratic function. Somehow it can do this as well. Linear SVM, however, cannot really classify the data if it looks like this because it only contains the linear boundary. The linear boundary cannot cut or maybe separate these data sample. However, if we change the SVM into some radial basis function, okay, I'll just this radial basis function will enable SVM to create like a curvy boundary, like a curvy or maybe circle boundary like this. And actually, if your data distribution is different, if it's not like a donut shape, but something like this, you can see that radial basis function can still help you classify. But the way it shaped the boundary would be kind of different from the linear boundary that you have on the left. So actually, you probably start to have a question, so what's the difference between this linear boundary and RBF boundary? Actually, the linear boundary or RBF boundary, they are not exactly boundary, but they're more like a mapping function. Okay, let me show you an example. So in support vector machine, let's say if you have the data that has 2 dimensions, like x is like containing x1 and x2, and you can provide a scatter plot that look like this, maybe this tree example. The SVM will first use like a mapping function to map this data such that it can separate the data between 2 classes. Actually, what I forgot to say is that these examples of the data are the data in the training. So we are learning how to classify SVM on training set first. Okay, so these are the data on training, but how should we perform a classification? How should we learn this classifier using this training data? So first we have to make this classifier know where to cut, where to classify, right? So the first thing that the SVM will learn is learn the mapping function. So from this 2D scatter plot, the mapping function would then map it to the 3rd dimension. For example, if the mapping function is a polynomial function like this, it could map your data distribution to be something like whatever on the left here, or on the right here. And then you can use a hyperplane to cut. And if you can cut it, that means you can classify. So the second mechanism of the SVM is to have the cutting hyperplane. So there are 2 things, mapping function and cutting hyperplane. Perhaps this example will be better. That is, if you have like a donut shaped data clustering. Like one class, the blue class, is the one outside, and the red one is the one inside. How can you separate the red from the blue? If you map the data with radial basis function, which is like an exponential function, using this function, you can then map the red points to those points that will float above, and the blue point would float below. That means that you can start cutting it using a hyperplane that would just cut just like this. So that is the two mechanisms of SVM. First, you have the mapping function. Sometimes we call it kernel. And then we have like a cutting hyperplane. But in the end, you will see that actually this cutting is just like a thresholding value. Or maybe a thresholding plane. But we will see it, yeah. It's likely very similar to that two previous case. If we have like a hyperbolic tan function, which is formulated like this, if you put x1 and x2 into its function, then this mapping function will make this blue point float above and the red point float below. And again, you can start forming a hyperplane that will cut like that. So yes, SVM is about mapping and cutting. That's it. So these are examples of how one might use SVM and how it's actually work. So I think if you think about this compared to what we learned before, like LDA, QDA, this is much more complicated because it not only has like a mapping function. This mapping function somewhat interact with how you make a judgment about the boundary, and then you have to have the boundary. So it has more steps. Yes, that's why it's actually turned out to be a big topic to learn. And actually not just that we are having this SVM to learn, we also have its dual optimization problem. So that means that's the reason why I didn't do the lab in Monday, because I find that there are so many things to talk about. Yeah, that's the reason. Okay, so now we know what is SVM, and when we compare to the rest of those previous things that we've learned before, we probably see that actually there are so many things to do in this one algorithm. Okay, first of all, what is SVM? Okay, as we know, SVM is a machine learning. It has the training phase and it has inference phase, just like other model that we learned before. That is, we have to train for the model parameters. After we have model parameters, we'll plug it in the function, the model, and then making classification. Before I go, let me introduce you a little bit. Let us focus on just the inference phase, right? And if you have like a model that look like this is actually what we call, similar to previously, the mapping function. This mapping function should map x into a certain region if x belongs to a certain class, and map x to the other region if it belongs to other class. Once it's mapped, then you can start to have like a hyperplane to cut it. So let's say, let us look at like a very basic example. Suppose that our data point, our input feature is a data in real space that is like just a scalar value, and we want to classify it. Let's say if this data can be linearly separable. What does it mean when I say linearly separable? It means that there's no overlapping between two classes. For example, if we have class 1, that is the blue line, blue dot here, and class -1 that is denoted as the pink point here, right? And if you put it on like a real scalar line, you can classify it by simply putting a threshold. Then you can get like a red and blue dot to be separate class. In SVM, we actually do something a little more complicated than that. That is, first we have to have like a mapping function fx. Actually, I should use a blue color. And this fx here will map the data points into different region. And that region will be represented by the value of that function. For example, it may map this pink point up to here. Let's say if it's mapped with some maybe linear line, right? And at the same time, it can map this blue point down here. This is the first step that we would do in SVM. And the second step, we will have a hyperplane to cut, right? So the normal hyperplane to cut could just be like a normal thresholding like this. So if you cut like this, that means you get those points above as class -1, those points below as a class 1. However, the problem is that even though you have like a one-dimensional data, you may not get like a very well mapping. Maybe you get something that, a little high up here and really, really close to the other sample that you map. So what would that happen is that then your thresholding or maybe your hyperplane will have a hard time, or maybe having a more difficult judgment to separate them. For example, if you map and it's kind of look like this, that means everything is in the same, like fx is above 0, and therefore your hyperplane start to have a hard time trying to separate them. So that actually become like a second criteria for how should we map and how should we cut. That is probably the best way to cut between these two classes is to find the closest point between two classes, that is this point and this point. Let's call the pink point here as point A and the blue point as point B. So probably the best way to provide the cut is probably to cut somewhere between these 2 points and cut it at this area where, like the hyperplane that you cut is the most separate from class A and class B. So it should be somewhere like that, like really, really between the two. Sorry. Because if you think about the fact that, okay, what if you don't want to do it like this? What if you do it otherwise? Like, what if you want to shift it a little bit? This means that if this is not in between A and B, like totally in between, if it's close to B, this means that it could misclassify class B to be class A, or if it's too close to class A, it will do the otherwise, but like the opposite, but probably have misclassified a lot. Or actually another thing that it should do, okay, if it's perfectly aligned between the two, it should somewhat, if you draw a straight line between A and B, somewhat as it tries to maximize the distance between the two classes, the distance from this hyperplane should be somewhat orthogonal to the closest. Therefore, it could perfectly balance between the two. So that's actually become like a second and third condition of this hyperplane. So let me summarize. First, in SVM, you need a mapping function that map the points into separate location. And second, you need a hyperplane to do the thresholding or cutting. And this hyperplane should be between the two closest points and also maximize the distance between those 2 points. Or on the other words, if I wrote a line here, it should maximize the distance from this and maximize the distance from this. Right? Okay. But the thing is, even though we have this condition, there could still be a problem if we use just like one set of thresholding. For example, if you are having points that align like this, and suppose that this red line is the line that separates the point into two classes, the problem is that you will have the point that nearly touch that line. So the boundary, let's say the boundary threshold of 0, what if you have a point that slightly move away from 0 and another one that's slightly below 0? Are you gonna say that these two should be the same class, or should it be different class if you don't know where it should belong? So this causes ambiguity in classification. That's the reason why they have to add another two thresholding function to make a better decision. That is, we try to move those points that used to be somewhere here, and we say because we can learn this function anyway, we can learn to map this one a little higher up and this one a little lower. And let's say we have like a good boundary of +1 and -1. And you know, if we see another blue point that is actually touching this boundary that we just made up, we can still tell that it's actually belong to the blue class. Okay, even though it touched the boundary, but that is because, well, with this additional boundary, it helps us save ourselves from having the ambiguity of the points that probably touching the line. Okay. Like this two is actually the ambiguity point because it directly touched the thresholding. Also, one more thing, we should keep in mind that, okay, given the fact that this is like a scatter plot of the data in 2D, right? The mapping function will actually extend the visualization of this data point in 2D into 3D, because as it would map these 2 points to different value. So if you consider all together, it becomes like a 3-dimensional problem. But it depends on how you want fx to be, like what are going to be the parameters of this fx. If the parameters is not good, probably the mapping will return the point somewhere that is still close to one another. But if you map well, you should be able to separate that point far away from one another. And as they are separate from one another, then you can get like a hyperplane to cut it. And with that, you can make a safe choice, like of what these points belong to and what that points belong to. So that is a mapping function and the thresholding. So now we know these two things. Okay, another thing, right now we are having example of x in 2D, input feature in 2 dimension or in 1 dimension. If you have x in 3 dimension, your SVM problem will be in 4 dimension because the fx, that mapping value, will add another dimension of your problem. So it's always like 1 + 1. Yeah. So yes, so your SVM will be in 3 dimension for this case. But in this, I think in this lecture, we will keep to this point. We won't go beyond. So how should we design the mapping function such that we can have a good boundary? This means that we need 3 boundary, kind of like 3 thresholding. The one in the middle, this one, and the one up here, right? And also the mapping function. So that is like 1, 2, 3 parameters, and the mapping function is maybe another 4 or 5, depending on what this mapping function is. If this mapping function is just a linear function, like fx is equal to w transpose x plus beta, this means that your parameters are going to be w and b and the thresholding. But Actually, in the very simple case, we will keep this thresholding value fixed and we'll only try to learn the bu and b in the mapping function first. But this mapping function has to satisfy certain criteria such that it can separately map the data points like this and enable the thresholding function to separate the class like what we just discussed previously. That is, maximize the distance between the two closest points, etc. Okay. So, another question that probably is important is how should we judge the distance between these points? Like if we say these are the two closest points, what is the distance? Actually, if you remember, we say we have a target hyperplane, that is this one, and we want to find the distance. We want it to be somewhere in the middle in between these two closest points. Therefore, we have to maximize the distance between this target hyperplane to those points, right? So in order to find that distance, we will have to use some of its property. That is, let's say if point XA and XB here are the two closest points, and you want to calculate, the distance that you want to maximize. Let's say if D1 is this one and D2 is this one, what you have to do is that you probably have to project XA on W, right? W is I forgot to introduce. If you have a hyperplane and the most important parameters in the hyperplane is a normal vector. And also because in this problem, as you want to use the hyperplane to map these two, you want to use a function to map these 2 points to separate and then cut with a hyperplane. Probably the simplest thing is to use like a mapping function that is the hyperplane itself. So you have a mapping function that is a hyperplane itself. Therefore, with this hyperplane, you have 2 parameters. That is the normal vector. The normal vector is the vector that is orthogonal to every point on the plane, right? The normal vector. And if you shift this hyperplane up or down, let's say if you move it up, your normal vector should still be the same. But what is different is like a bias constant, or maybe some constant value that will move it up. So let's say if your hyperplane was accidentally touching the original point, then your hyperplane function should be W transpose X equal to 0, right? This is your hyperplane at the original point. Maybe just put it like this. If you lift your hyperplane up, maybe lift it up by B value, maybe just shift it up vertically, then your hyperplane that you shift it up will be and Y it has to be equal to 0. Do you remember? Every point on the hyperplane will because we say that the view here is the normal vector. When it's normal, that means it's orthogonal. If those points are in the hyperplane, that means every points are going to be orthogonal to that. Therefore, for every x, and here's example xc, for every x in the hyperplane, X transpose W has to equal to 0. If this hyperplane touch the original point. But if you lift your hyperplane up, that means you have some kind of constant add up. So that means you will then change your function to be plus b equal to 0, right? So that what's a hyperplane? What are the points on the hyperplanes? Okay. So this is your hyperplane function. And your hyperplane function will now have to perform two things. First, it has to map your points up, down here. And second, it has to be that hyperplane itself that cut. And third, as we mentioned before, it needs some kind of additional boundary to make sure that you can well separate the samples from two classes. So this means you are having three hyperplanes, right? Because one is for class A, another one for class B, like that additional boundary. For class A, this one is for class B, and the one in the middle, that is like the original place where you want to make a cut, right? Actually, we have a name for it. The one that is up here and below here, we call it support hyperplane. Meanwhile, the hyperplane that we actually use to make a cut is called the target hyperplane. So yes, there will be a lot of jargon in this SVM because we need hyperplane mapping function and the hyperplane that we use as an addition. So yes, lots. Yeah. Anyway, as we can see, the support hyperplane, target hyperplane will be somewhat parallel to one another. This means that if you draw a normal vector to those hyperplane, it will be the same normal vector. But what is difference between them is just like a shifting value, right? And as we mentioned before, we want this one and this one to be somewhere +1 and -1. So you can guess that whatever shift is here is like going to be the shift with the constant +1 and -1. So in fact, for this one, you can say for every point on this hyperplane, it's going to be x transpose w b, x transpose b plus b, +1 equal to 0, and this one x transpose something like that. Probably what I wrote it here is kind of swapping the direction, but that's okay. Anyway, so now we know we have three hyperplanes. But what are they, right? What is the function? Concretely, the function for the target hyperplane will say that whatever points that if you map it and the value is greater than 0, which even though it's higher than that support, it's also higher than this target hyperplane. So that is all positive value, so you can judge it. And whatever that was less than 0 is negative here. Actually, you can strictly use like a sign, like a greater or less than, without caring whether or not it's at the 0, because you had a support hyperplanes to help you judge anyway. So it shouldn't come closer than this boundary. And for the targets, for the supports, then you will have these two lines. One is above 1, another one is less than 1. Yeah. And as you have all of these, now you have hyperplane, you have mapping function, what you want to learn for the model parameters, that is the bu and b. So that means that all you have to do is to optimize the bu and b such that you get the mapping function, the hyperplane that satisfies your condition. So altogether, you can provide actually an optimization problem to find the view that maximizes the margin between the support hyperplane. And also that support hyperplane has to map the data to the right location, which become this constraint, but I will describe each of these. Okay, for the distance between the hyperplane and the support hyperplane, as I mentioned before, they are the distance, let's say from point X here, okay, maybe from point X here to the target hyperplane, and you want to compute it by projecting on the normal vector, right? Right? And another one that was for the support vector that is below here, and now you have to negate the normal vector of that hyperplane because it's opposite direction. And then you have the point B, and what you want to do is to add up the distance. So your total distance from here to here, D is D1 plus D2. So with that, you can compute this as W transpose XA and minus W transpose XB. Actually, if you don't have a hyperplane, I mean, if these two supports are not hyperplane, probably you cannot really tell the distance. But because they are the hyperplanes, you know that every point on here will have to be orthogonal to that normal vector. Then you can use the property of the hyperplane to find the value. And also another thing is that the vector W here is our unknown that we have to learn when we train SVM. And when you try to learn this unknown, that means that when you do the optimization, you probably initialize the view with some random value. So that means that initially when you start doing SVM, whatever you get here is probably like the view that rotate and having some random value. Therefore, in order to prevent any underflow or overflowing problem, that the view could be too small or too large, they will usually normalize the view in the process. So with that, as you normalize the view here, you can further derive what the distance should be like. So first of all, X transpose the view here will be 1 minus B. Actually came from this function. Add up with this one, that should be minus 1 minus B, but because you have the negate, then you have, right? And the norm of the view. Therefore, as you can see, this B and that B will cut each other off. Then what you get is the view divided by norm of the normal vector. Okay, that's it. And as we mentioned before, our target for learning this SVM is to maximize the distance so that this target hyperplane is lying in between. So this means that you have to maximize this distance. So that becomes our objective function, main objective function. So we want the view to maximize this value. And then, please don't forget that we also need this mapping value to map X to the right place, right? And as we know that, if we put X in this support hyperplane, and it mapped it to the right direction. Suppose x came from class 1. If it's mapped to the right direction, it should map to value greater than 1. And if you multiply that class value of that point A with the function itself, you should have a value greater than 1. For the points in the other class, that is xb, if you put xb into this function, you get a -1 less than value. And of course, the value corresponding to that class is -1. Therefore, if you multiply -1 with less than or equal to 1, then you get greater than 1. So you can try. You want to try? Okay. This one, FB multiply with -1. If you put the negative, sorry, how should I do it? Oh, no. This one is less than -1. This one is equal to 1 when you multiply greater than 1. Okay, so as you can see, whatever class that x came from, it will always multiply by y and have a value greater than 1 for both cases. So that becomes your condition when you optimize for the B and B. So that is like the condition that you get it here. And please notice that this condition has to be satisfied by all of your training samples. Let's say if you have 1,000 samples, you will have these 1,000 conditions to be met. And this is relying on the assumption that your data samples are linearly separable. What does it mean if your data is not linearly separable? That means that, okay, let's say if you have a hyperplane like this, there will be some of your data point that actually go below here, or there's some points go up here, loop points. So it's like there's some kind of mixing data points that is non-linearly separable. So as you have this optimization problem, you probably know by now that, well, this maybe first formulation of SVM will have some kind of problem if your data is non-linearly separable. Okay, but before we go to that, we actually have solution for that and we will learn it today. But before we go, let's recap a little bit. This is a concave function, right? 1 over norm is a concave function. And you do the maximization, therefore this is a convex function. And if you do something equivalent, that is to do the argument min, the bill still the same. But this time we do the we do the argument min over the square of the L2 norm of the vector W. Then this is still a convex function. So I kind of say convex concave here because when we decide whether or not we can turn it into Lagrangian and what kind of solution we will have, it will tie to this convexity concept. Anyway, just to recap. So yes, you can somehow reformulate this problem such as this as well. That is, you have this main objective function as the argument min of the L2 norm of the the normal vector W, and you still have those conditions following your main objective function. Thing is, normally people would write it, we will use this notation to provide the formulation for SVM, which becomes our next slide here. And as I mentioned before, this SVM problem assumes that our data sample is linearly separable. What if it is not? All right. If it's not, it will be somewhat difficult, right? Because that means you cannot find the data sample that will all satisfy your constraint. Well, in fact, you can change your constraint by changing this value. For example, if we go back to this slides, because we say that our support has to be somewhere up 0 and below by, up by 1 and below by 1 from 0. So that means this value 1 here is like the size of the boundary that you want. So if you want it to be further separate, you can change this value to be somewhere larger, and it will not, it will do the same mapping. That is, if you think about in these slides, if you change this value to be, let's say, 2 and this one to -2, and your class belongs to class 1 and plus 1, you still get the same types of condition that is greater than a constant. So this means this value 1 and -1 is like, it's actually a hyperparameters that you can further tune if you want the boundary to be large or smaller than 1. But also, this boundary kind of enforce the fact that your data has to be, like if it belongs to that class, it has to be in one side, not the others. So it has to be linearly separable. Therefore, if you want to use SVM for data that are having some kind of outliers that is not perfectly linearly separable, what you can do is that you may relax the constraint, these constraints a little bit. That is, for example, actually not example, but it's actually the algorithm. That is, we will add what we call a slacks variable. This one denoted by set j. Notice that j is the indexing value for all of our training samples. That means that every training samples that satisfy this condition can be relaxed by this set j. So set j will allow the mapping to be maybe in a wrong side. For example, if the zj is larger than 1, it will allow us to use the point that is crossing to the red side. The blue point that crossed to the red side, or the red point that crossing to the blue sides, to be something that we can consider. And then our hyperplane can still lie in between most of them. So that is like the additional feature that people sometimes do in order to allow SVM to be used with the data that are non-linearly separable. So slack variable is one of the trick. But what you should also observe is that actually as we add the slack variable, this slack variable is also included in our main cost function here. And therefore it has to have some kind of like a regularization parameter C here. So this parameter C will somewhat control the impact from your slack variables. Okay, let us consider the case where this entire term is small, very small. And it is small because of set j, right? If set j is small, this means that this go back to the original SVM, where you don't allow any points to cross between the classes. Therefore, your optimization problem will try to solve a strict SVM problem. But if your set j is large, that means you enable some relaxation, right? So as I mentioned here. But C constant here will have a little slightly different impact to your optimization problem. That is, if we, let's say, if we fix the value of C times sum of set J here, let's say we fix it to a value equal to P. We fix P value. If we increase C, that means we will reduce sum of set J. What would that happen? That means that we will go back to restricting the boundary crossing. That means we go back to the original problem of the SVM. That is, if we increase C, so that go back to this case. That means our boundary will become small because it tries to minimize the effect of the crossing. But if this C value is small and we still fix the value of P, then sum of set J here will be large. That means you enable the relaxation and therefore you get a lot of crossing. You allow the boundary to be very large. So that is something to keep in mind when you use support vector machine. Actually, if you use Python and if you try sklearn, they will allow you to put in the value of the constant C here, and it will using this slack variable optimization problem as the main optimization problem to solve for SVM. And actually, when we use slack variable like this, we call it soft margin SVM. Or on the other words, most of the SVM tool that we use today will be the one that is based on the soft margin SVM. And actually, the original SVM that we've learned previously, that is without the slack variable, this one, is what we called hard margin SVM. But the problem with hard margin SVM is that if your data is non-linearly separable, it will not be able to find you the hyperplane. So it's like none of the data samples satisfy that condition. So that's the thing about SVM. And yes, actually here are just example of what it's like. If you know that hard margin SVM cannot be used with the case that data is crossing one another. Actually, it starts to have problem even when the data wasn't crossing, but nearly there. So if you have some kind of outliers, like in this example, you only have this blue point as the outlier. And because when we learn the margin, we want that margin to be in between the two closest points. Therefore, this point will highly influence how your hyperplane is cut. And therefore, it will shift the location from where it used to be to here, that is tilting dramatically. And sometimes, if you have so many outliers, such as this one, where initially you have only one point, it changed the decision. If you have more points, it further changed decision. What's going to happen is that if you still keep using this hyperplane, the problem is that the area between this point to the hyperplane is very close. That means that if you use it in testing phase or when inference, very likely you're going to misclassify. And that's because your SVM wasn't considering the fact that there may be some outliers in your training samples. On the other hand, if you use the soft margin SVM with the samples like this, the soft margin SVM will have some kind of mechanism that is enabled by the slack variables to not consider the points that could be outliers. So it will be able to give you this beautiful lines just like this, even though your data sample are really crossing one another. And that's because slack variable will allow us to use that point even though it crossed. So that's like a benefit of having slack variables. That is for you to ignore those points. However, I remember that we've learned about outliers before. Actually, there are like two solutions for you to choose. First, you can choose to remove outliers with those two that we learned and then use the original SVM. Or you can still use all the data without considering them as outliers, but instead use the soft margin SVM to provide the hyperplane and the mapping function. With that, you can still have the SVM to function as it should be, despite the fact that your training samples contain outliers. Yep, so that's it for today. Actually, that's all. So what I would like you to go back home and recap was to somewhat review the following, jargon. First, what's the margin? The margin is the area between two supports, hyperplanes. What's the support? Supports are the points that are on the hyperplanes that we add up so that we don't misclassify, right? What is hard margin? Hard margin is this original SVM problem where you don't consider the fact that your data may be overlapping. Like you assume linearly separable data set. What is soft margin? The soft margin SVM is the SVM problem when that we start to consider the fact that there may be some overlapping between data points, and therefore we have slack variables that we add up so that it relaxes the constraint of the original SVM. What is slack variables? That is this variable that we just added into the soft margin SVM that enables some points to cross over and mixing into the other classes, but we will pay less attention to those samples. What is regularization parameters? That is the weight, right? The weight between the term of slack variables and the distance minimization. And lastly, does any of these remind you of LDA? It probably does, because LDA is a linearly boundary separation, but SVM has linear separation and hyperplane cutting. Okay, that's it for today. For your next week, if you enroll the course on optimization, have you? Okay, we probably go through some dual problem. Actually, I will just provide you some heads up. This on the left-hand side is our previously learned SVM soft margin. Actually, we can turn this problem into another equivalent problem. That's what we call dual. Dual is just like an optimization trick to change your optimization problem into something that is easier to solve, or maybe enable different feature. Actually, for SVM, when you convert it into a dual problems, a lot of students require like this because they don't know why it's so hard, why we have to learn it, but I have an answer. A quick one is the fact that it's more efficient. You will learn that some of the parameters will always most likely have like a solution that has value of 0. So that means when you have a lot of 0, you can cut off that information. You don't need to operate on that. So it's efficient. It enables some kind of efficiency. Second is the fact that it's actually enable a different feature that is what we call kernel. It's actually a new mapping function that we've just introduced to you early in this class, that you can have radial basis function, hyperbolic tan function to map your data sample that is so complicated so that it can spread them from one another, separate them. And actually that came from the benefit of this kernel function. Or on the other words, those functions that you've seen before, and maybe you can remember, they're actually the kernel function. They are the mapping function that's actually hidden here. And actually for the SVM that we just learned previously, it is very much, we can say that actually that one is like mapping with a linear function. While for the others that is more complicated than that, you can enable them by using dual problem so that you can use various different functions to do the data mapping. Therefore, you can cut them with a thresholding or hyperplane that is much simpler than before. That's it for today.